Okay, well, okay, we're back, all rested from the holiday. First, I always ask for questions. Are there any questions you've come up with so far? By the way, you're aware that I have office hours before the Wednesday and Friday classes, say from 1:15 to 2:15 or so, in my office, 388 LeConte. You're welcome to come and chat and talk about anything, which I think is a good idea if you can. By the way, I would have you make sure you look at the schedule of exams. There's been some jiggling around of the times. The times will be, there are the midterms. I don't remember exactly the date, but they're on Wednesdays. The original thought was having 7 to 9 p.m., but apparently the registrar wants us to use 6 to 8 instead. So we're using the Wednesdays from 6 to 8 p.m. It was 7 to 9, but that's wrong now. But the date is the same, and now we also know the rooms. It's all now posted in an updated syllabus, so you can check the syllabus and make sure you don't show up at 7 o'clock. That's the main message here today. All right, so again, no questions? Okay, now last time I sort of went into a rather long-winded introduction, and I today will move along rather more briskly. This is let's get the this is again the outline of the chapter, and the topics I want to cover today are these and numerous, and we have to move unfortunately fairly fast. The main point is I want you to first of all understand what is the concept of a charge. It's just a quantity of electric stuff. We don't, as I say, we don't know exactly what this electric stuff is, but it's part of nature. It's crucial because it makes up atoms, and also the attraction of things to each other is through this electric force, as you know. So, for example, atoms are held together. We have a proton, electron going around. The reason they hold together is because there is an attraction between the negative electron and the positive proton. Why it's like that, we don't know, but that's what nature has presented us with. So, but I want you to understand that charge is a quantity of stuff. Don't get it confused with current, for example. A current is the movement of this charge. Sort of, again, the analogy that I used is that of water, where the quantity of charge is like a quantity of water. The best analogy to a coulomb of charge, the quantity, the unit coulomb of charge, is a mole of water. The unit of mole. Because a mole contains, 6 times 10 to the 23 molecules of that type. Molecules per mole, right? Likewise, with charge, we have a similar number. I forget what it actually is. Sometimes it's something like 10 to the 16th electrons. The electron is the basic unit. Don't quote me on that, but it's electrons per coulomb. So just as molecules, say water, H2O, there are 6 times 10 to the 23 of those in a unit of mole, there are that many electrons in a coulomb. The actual charge, that one I do remember, is 1.6 times 10 to the minus 19. So the reciprocal of that is, this is the coulombs per electron. If you took the reciprocal of that, it would give you the number of electrons per coulomb. So maybe I put a question mark there because I don't remember that number. This one I remember. Okay, so the point is that this charge, as we've observed it, always in isolated charges, we've never found anything other than this unit. It's quantized. It's always this amount, whether it be an electron or proton. We have these charged particles that are created, mesons and this and that. They always come out somehow this. I think there's some very deep fundamental reason for that, but I don't know that physicists have yet deeply understood why it's always that, but it always is. Now, you may hear of something else called a quark, which is 1/3 of electric charge, but we've never been able to isolate a quark and actually see something with 1/3 charge. They always come in with such a strong force that they combine such that there's like 3 of them, so they add up 1/3, 1/3, 1/3 to give you 1. Or they'll cancel in some fashion. There may be 2 plus 1/3 and minus 1/3, but in the observable realm, there's only full charges. And again, that's one of the mysteries of nature, but we take it as a fact. And also, we don't create or destroy charges. You can do things like destroy 2 at a time. For example, if an electron and a positive electron, negative and a positive electron come together, they will annihilate each other. So it started out plus and minus, namely total 0. Poof, again total 0. And you can create things too. Sometimes you get enough energy, you shoot enough energy. With enough energy, you can create a pair. They'll always come out of plus. You started with 0 charge, poof, well, bang, you'll get plus and minus, equal amounts. So charge is conserved. And as far as we know, the universe as a whole seems to be pretty much neutral. There's as many pluses as minuses. Again, that's probably a good thing. If it were heavily charged, things would sort of fly apart. And that wouldn't be too good. Of course, there may be a slight unbalance. Like if there were 10 extra electrons in the universe, it probably wouldn't upset things too much. I don't think anybody's measured the net unbalance of any charge. But it's possible. It depends on the limit of your accuracy. And the fundamental thing is that, as you of course know, is that if you have plus and minus, the pluses will repel each other, and the plus and minuses attract each other with equal and opposite forces. So we say that like charges repel and unlike charges attract each other. This is not news to you. But I really like it because, a lot of people put the word like as a punctuation. It's like a nice day. I think like I'll go to the store. So here's a chance to make the Guinness record of like. Like it's like unlikes like repel and no likes like repel and unlikes like attract. How many likes in one sentence? Is that a Guinness record? Call them up. Personally, I'm not fond of that manner of speech, so I have to make fun of it. Sorry. Anyhow, so we have these likes and dislikes. But so one of the things that we're going to use as a qualitative thing is that if you have a lot of similar charges together, they're trying to get away from each other. If you have dissimilar charges, they want to go to each other. And if you have a lot of similar charges and they have any avenue of escape, they'll try to get away. And we'll see that. Oh, I showed it to you last time with the Van de Graaff generator. Remember, we charged up the Van de Graaff, and I brought another globe near it. Now, what was happening? The Van de Graaff, if we do it again, got charged up with a lot of the same type of charge, and they don't want to be together. See, like if I had this big Van de Graaff here, and I'm bringing up charges, I'll explain. I have all kinds of charge over here. They hate each other. They want to get off. Now, if I bring over a path where I can bring them to what we call to ground, in other words, any way out, they will jump across, and that was the spark. That was that spark that we drew. So this is just obvious, but it explains why things happen. We'll see that. We're going to see things like, for example, you bring more than I just do it. Here, this is called an electroscope, and for those of you, unfortunately, who are sitting way in the back, you may not be able to see it, so I've drawn it up here. What is it? It's a metal rod that's shaped like this. That's this thing here, and then we have this movable arm. I hope I've drawn it right for you to say. Okay, so the arm likes to sit like that. Now, suppose I create some electrostatic charge by rubbing these things. It's our primitive way of getting charge. Now, this material from here down to here is an electrical conductor, so the electrons can move rather freely. So if I bring electrons close to them, they are going to run down the rod and run up onto this rod here. So there'll be negative guys who've run away here and negative guys that have run as far as possible here. You'll have negatives and negatives near each other, and they want to avoid each other so that the rod runs away, the movable rod runs away from here. Okay, so that's a simple thing. Now, suppose I give them a chance to get off. Let me try it again. I'm going to give them a chance to get off the electroscope by drawing them off. Maybe I do it with my right hand. Okay. Now, I draw off the charge. So I've made any guy who wanted to escape has escaped. But in order when he escaped, he left behind the positive charge. So now this thing is positively charged, and it repels itself. Get that? This is what's known as inducing charge. I induce it by bringing this guy near, and it leaks off because it's humid in here. So you want to understand on a very simple basis, and I think there's some homework on this, very simple idea. Namely, if you have similar charges, they will repel. And if they have a chance to move, they will move away from each other. In other words, if I create negative charge here, any negative charges on this rod will try to get away, and they will run as far as possible. And that means they will accumulate down here and run away from each other. Simple as that. Now, this, I wanted to show you, I have it here somewhere, a very interesting paper. I refer to it in my notes. Oh, yeah, here it is. By some professors here on how they read DNA. Let me see if I can find it in this collection here. Okay. Oh, here it is, yeah. This is a very interesting thing. I think it's Jay Grove. Anybody work in his lab by any chance? No, okay. But the point is, you would know better than I, but apparently this double-stranded DNA has twice the negative charge of single-stranded DNA. That makes sense. Two strands, each one carrying negative charge would make it double. So what you have is more of these, like, I guess, single strand, and then you have two strands. Okay, now what they have somehow done is they've made little silica balls that they've somehow charged up with a negative charge. So, and then they spread the DNA on some kind of a plate. And if it's doubly stranded, where's my arrow? You have twice as many negative charges, and so the spheres float above it because their weight is pulling them down. The repulsion of the electrostatic repulsion is pushing them up, and so they float. But on the single-stranded ones, if you put a sphere of the same type, it's less electrostatic repulsion, less force, so the thing will go even lower. So they can sort of see where it's double-stranded and where it's single-stranded by just measuring the height of these little balls. It's nice. At least I got a published paper out of it. If you want to read it, you're welcome to it. So, so that's just a qualitative use of these electrostatic effects. But then the quantitative experiment that it was done very early on when people started to be serious about electricity, which, by the way, was really around the year 1800. I think in the 70s, see, up to that point, it had been sort of like this. You rub two things together, you get a little charge. But then the Italians, Galvani and Volta, discovered that if you can make a battery, an electric battery, so you can create electricity more or less on demand and reproducibly by having different metals in a solution. There's a famous experiment where Galvani had one of these things and he touched the frog's leg and made it jump. And the question was it because of the frog or because of the electrodes or what? But anyhow, they realized that you can make electricity in a reproducible way. And at that time, that technology allowed us to study it in great detail. So then the really important experiment then was to measure with known amounts of charge what is actually the force, say, of attraction between these two. And of course, it's given by, obviously, proportional to the charges that you put there, the amount of charge, the coulombs, Q1 and Q2. And then he measured it as a function of distance and found that it fell off as a distance between 1 and 2 squared. And then to make a force out of it, you have to have some kind of a proportionality constant, because this is coulombs, this is meters, say, squared, and this is a unit of force. So you have to have something that converts that, and also gives you the magnitude, because these are measured one way, and the forces you measure you get a third way. And it turned out that the constant that they got was 9 times 10 to the 9th. And what it could simply be is newtons per coulomb. No, that wouldn't be right. Coulomb squared, and you have to have an r squared of your meter squared. Right? Because you got to come out with newtons at the end. So this is meter squared, and that's just an experimentally determined thing, and it depends on the units you use. Okay, so now newtons is not a particularly familiar unit to you, I dare say. I mean, you saw it in 8A probably. But when was the last time you said, "Give me 1 newton of beef," in the butcher shop or something? You don't. Actually, there's a lot of confusion because let me just try to straighten this out a little bit. This is from 8A actually. Because we have different units. We have units of mass, and we have units of weight. Which weight is a force. As we said last time, your weight depends on the gravity force. So what are the, let me just see, I wonder if anybody really knows here, what are the units in mass in the scientific system? We call MKS, meter kilograms second, or mass kilograms, or meter kilograms second. The unit of mass, kilograms, right. And the unit of force or weight is newtons. Named after the fig of the same name. Now, but we have also the English system, which is the one we use in our daily lives for the most part. Now, the easy one is the unit of weight in the English system. That is pound, right? Pound. Pound of weight is a force, a pound force. The less familiar one that we never use in real life, there is a unit of mass in the English system. Somebody know? Say it louder. What, slug, did you say? Did you say? I hope you said slug. Believe it or not, yeah. See, this is a unit of mass or inertia. And slug, that sounds pretty good. I mean, that's rather sluggish. Yeah, mass is inertia. Mass refers to inertia, right? This is a tendency to go in a straight line and not change your speed, whereas weight is a force. So the unit of, I won't go into slugs particularly, but there has to be a unit, but we don't use it. But so if you want to convert, see, this is really unfortunate, because if you go to Europe, you'll buy a kilogram of beef. You're not buying a weight, you're buying actually a mass. But a kilogram weighs a certain amount of newtons. You can figure that out because you use F equals ma. So if you have 1 kilogram, and the acceleration of gravity is 9.8 meters per second squared, this represents 9.8 newtons. So a kilogram weighs 9.8 newtons. Very unfamiliar stuff, because unfortunately in our real lives we mix these two. But you see, I think you can see the logic of these two things have to be different. In any case, a newton of weight, of force, is about 1/4 of a pound.